this fourth one is similar to the third exercise, which we solved in the previous linear algebra video. The only difference is that there are now 3 diagonal blocks instead of 2. So it's similar. We have these positive integers n1, n2 and n3 in this fashion, and so are m1, m2 and m3. Then this block diagonal matrix is similar to this block diagonal matrix if and only if n1 and m1 are the same, n2 and m2 are the same, and n3 and m3 are the same. So let's see the solution, and the solution is also similar. You already know that one half of this double implication is obvious. Namely, if these are true, then these two are similar because they are the same matrix. So let's start with that. If n1 is equal to m1, n2 is equal to m2, and n3 is equal to m3, then the given matrices are the same and hence similar as well, because similarity as an equivalence relation is also reflexive. Conversely, let they be similar. Then obviously they should have the same size. Otherwise, being similar does not make sense. Which means that n1 plus n2 plus n3 should be equal to m1 plus m2 plus m3, like that one. So there exists an invertible matrix A, which say has Aij as its ith row, jth column entry in Fn, where n is the common size plus n3 equal to m1 plus m2 plus m3. Such that, so now we write the similarity relation. A times the first matrix n3 times A inverse is equal to the second matrix. Or A times the first matrix is equal to the second matrix times A. Now also you know what to do next. We are now going to calculate this product and this product. And if you remember from the previous solution to the third one, we need more horizontal space to write this product and more vertical space to write the second one. So So let's now start writing. So we are going to first of all write this product, and it's going to take so much space. Let me start here itself now. A times M1, N1, N2, N3 is equal to, the pattern will be exactly similar to the pattern you already saw in the third exercise solution. So things are very familiar to you. Still, in spite of this familiarity, keep in mind that whatever I write here, you have to verify on your own. That's because obviously I may make some mistake, some small mistake. So if you find a place in any of this, not just here, in any video, if you find a place which is not really clear, it's difficult to understand, or something outright false, wrong, please let me know in the comment section below. So the product is going to look like this: 0, A11, A12, A1, N1 minus 1. That's not the entire row. There are more things to write, but we can only write this much here. So let me write that portion of the next row: A21, A22, A2, N1 minus 1. 0, AN1, AN2, AN1 minus 1. Okay, so that's how the matrix only starts. We have actually shown all the rows, but not fully. The pattern that this second index is following, according to that pattern, in the next column we should have N1, but that next column is a 0 column. I can in fact write the zeros here itself. And then the next column will have N1 plus 1 as its second index. A1, N1 plus 1, and like that it goes. And here also we won't be able to completely write the matrix. Another part will be needed, because just like this portion, this is also going to stop at N1 plus N2 minus 1. Okay, so it started with this second index N1 plus 1, and then we increase the second index 1 by 1 and reach this one. Like that, the same portion for the other rows are these. N1 plus N2 minus 1. AN, N1 plus 1, AN, N1 plus N2 minus 1. And then the next column is a 0 column again. And it continues further. So according to this pattern, here you should have the second index N1 plus N2. So in the next column it should be N1 plus N2 plus 1. N1 plus m2 plus 1, and it finally ends with n minus 1. Did you see why? Actually, we saw this in the previous solution also. That's because, it doesn't end with n, because already we started with a 0 column, and then the indices started, the second indices started with 1. So it should end with n minus 1. You cannot write n, because then there will be n plus 1 columns which are not available. A2 n1 plus n2 plus 1 A2 n minus 1 n1 plus n2 plus 1 n minus 1. Ironically, I said that it needs so much horizontal space, but because we have only so much space, so eventually it took all the vertical space also. Okay, so that's my this product, the left hand side product. Now what about the right hand side product? The right hand side product is going to need vertical space. And here also, although we don't need really too much horizontal space, that is this product, but like this, the indices are going to be so big that eventually we will need space fully. Okay, so it's going to look like this. And M1, MM2, MM3 A is equal to it starts with A21. You may remember this pattern from the previous solution. It starts with the second row of A. Oh, yeah. I should write it somewhat far away from this one. You will understand why. A to n. We do have all the columns, however, 1, 2, 3 up to n. A31, A32, A3n. Like that it goes. And at one stage we reach M1, AM11, A M12, A M1n, and then after that we have a 0 row. Then the next row is M1 plus 2, 1, M1 plus 2, 2, M1 plus 2, n. It's that we can write these things that I needed this space. And then it continues like that, and eventually reaches AM1 plus M2 1. Just like you reach this M1 stage, after that you have a 0 row. After that you reach at some stage M1 plus M2, that index. A M1 plus M2 M, and then again another 0 row. So won't be able to fully write the product here. That means I have to erase this one. But if I erase both the matrices, then what can I do after that? Luckily, what follows after this, after writing these products, is the same calculation that you saw in the third exercise, but only extended this time. So there is nothing wrong if we do not keep it. We can, however, write one more row, cramming everything. So the next row, according to this pattern, should have the first index M1 plus M2 plus 1, but it's a 0 row. So that one after that should have first index M1 plus M2 plus 2, 1, A M1 plus M2 plus 2, 2, and like that A M1 plus M2 plus 2 N. But then it continues even after that, and eventually reaches this stage A N1, A N2, A N N. However, that's not the last row. Note that the first row corresponds to the first index 2, not 1. So that means the row number is 1 less than the first index. So this is the row n minus 1. There is one more row. And that last row is the 0 row. This is the entire matrix. We were not even able to complete the square brackets there. We have to complete them here. Okay. Now, if you go back to the solution of exercise 3, there you will see that after writing these two products there, not exactly these two products, but the products that we have in that problem, we then went on showing that these entries are all 0, and they are the entries in the m1th row of the matrix A. So that's how the matrix A had an entire 0 row. So how can it be invertible? That was our contradiction. The exact same thing we are going to do now also. And the first part of our calculation will be identical to what we had there. And that's why I said that there is nothing wrong if we erase these parts. You will, of course, have to go through this entire thing. I mean, you should, and see that, yes, this is also exactly identical. At least it starts like that, but then there are some other parts which did not appear in that solution. But still the pattern is same. And we start our argument now like this. This part also is just like that one. if, so this is our supposition. What we now suppose, what is our aim? We want to prove that n1 is equal to m1. We start by supposing that m1 is greater than n1, and then something goes wrong. Okay, so here also same. If m1 is greater than n1, then m1 is also greater than n2 and n3 as well, because we already have these inequalities. Now, following the same argument that we followed while solving exercise 3, we immediately notice that am11 is equal to 0. You actually know the reason, because this is a first column entry in the matrix, in this matrix, of course. And because this matrix is equal to that other product whose first column is a 0 column, so am11 is equal to 0. Next, am12. When we were solving that one, we saw that this becomes equal to am1 minus 1, 1. It is equal to that other entry where the indices are both 1 less than the corresponding indices in this entry. That is, you can subtract 1 from both the indices and you have equality. But this is again a first column element, so this is equal to 0. And the argument proceeds like that. And at some stage, you reach n1, the second index n1. As you start subtracting 1 from both the indices, you get next this one, but then you follow that pattern. And what you want to do, you keep on subtracting more and more ones from n1. You want to make this n1 1. For that, you have to entirely subtract n1 minus 1 from n1. And the same thing you have to subtract from m1 also. Do you recall that this is how we argued in the previous solution? So if you subtract n1 minus 1 from m1, you get m1 minus n1 plus 1. And the second index becomes 1. So that's how you also get 0 here. But the calculation doesn't stop here. Also, so next what we should consider, we have considered the second index n1 up to n1. So the next one should be n1 plus 1. And this is immediately equal to 0. Again, by the fact that those two products are equal. And then am1 n1 plus 2. This is m1 minus 1 n1 plus 1. The moment you have second index n1 plus 1, this is equal to 0. And this part of the calculation also proceeds like that. And here, eventually, I should rather be very careful in writing these things. I should not write something wrong, because already these things are so complicated in terms of having these indices. It's very easy to make mistakes. So in the second half of our calculation, we start with the second index n1 plus 1, and we are going like this. And eventually, we reach this m1 n1 plus n2. This is like this one. Okay, starting from 1 you eventually reached n1. Then starting from n1 plus 1 you eventually reached n1 plus n2. It's as if here again you are starting with 1 and now you reached n2. m1 minus 1, n1 plus n2 minus 1, and like that we keep on subtracting 1 from both the indices. Now excuse me, we want the second index to be n1 plus 1. So what should you subtract from this to make it n1 plus 1? You have to subtract n2 minus 1. If you subtract n2 minus 1 from n2, then you will get 1, so that will become n1 plus 1. n2 minus 1 you have to subtract, okay. I am actually thinking of it again because if I want to see if I have written the thing here correctly. I am subtracting n2 minus 1 from this to make it n1 plus 1. So from this one also I have to subtract n2 minus 1. So that will give me this, and the second index becomes n1 plus 1. Is that what I have here? m1 minus n2 plus 1 and n1 plus, yes, okay, fine. But things don't quite stop here also. Also, because more columns are there. So after that, we will naturally consider which column, which second index, n1 plus n2 plus 1. And that is immediately 0. Again, this follows from the fact that the two products are equal. m1 n1 plus n2 plus 1 is equal to 0. Next, n2 plus 2, this is equal to m1 minus 1 n1 plus n2 plus 1, but that's again 0. So in this final 1/3 of the calculation, eventually what do we get? We get to n1 plus n2 plus n3, which if you see is nothing but n. From this one also, from both the indices, we subtract 1 first, and the pattern follows. Okay, so this time in this third 1/3 of the calculation, after that also, we want the second index to now be this, n1 plus n2 plus 1. But what do we have here? We have n1 plus n2 plus n3. We want to make n3 1. So we have to subtract n3 minus 1 from this. And that same thing we have to subtract from m1 as well. So m1 minus of n3 minus 1, so minus n3 plus 1. And this then becomes n1 plus n2 plus 1 and that is equal to 0. Again, let me check what I have here. M1 minus N3 plus 1 and N1, yes, okay, yeah. So finally, we have shown that all the entries in the row M1 of the matrix A are equal to 0. Thus, all the, or yeah, instead of writing in words, I can simply write in symbols. A M1 J is equal to 0 for all J from 1 through N. But then A is not invertible a contradiction, and this contradiction arises from our starting point, from the supposition that M1 is greater than N1, so it cannot be true. Hence, M1 has to be less than or equal to N1. Similarly, M1 also has to be greater than or equal to N1 by a similar argument. Thus, M1 is equal to N1. Okay, but that's only 1/3 of what we want to show. We also have to show that M2 is equal to N2 and M3 is equal to N3. Next, suppose M2 is greater than M2. Don't be afraid, we are not going to do all the things with this one as well. Then I will just tell you what to do and you do the rest. Then M2 is also greater than or equal to N3. Now, arguing similarly as above, one can show again that a row of the matrix A is 0, but the question is which row? This time the row is row M1 plus M2. J is equal to 0 for all J. But then again, A is not invertible. So again a contradiction, so that means this supposition is also wrong. Thus, M2 must be less than or equal to M2. Similarly, M2 must also be greater than or equal to N2. So, M2 is equal to N2. Yeah, now it's very easy to prove that M3 is equal to N3. Because what is M3? M3 is N minus M1 plus M2. Now M1 is N1 and M2 is N2. So this is N minus N1 minus N2, but that is N3. So that's how we have proved the more complicated implication of the double implication. And this completes the solution. So that's just it for tonight. Tomorrow also we have our upload, and we are going to start a new section in Riemann integration. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.